Okay, and welcome back. We are going to talk about today chapter 7.2, which deals with how to estimate a population mean. And as you saw before in the section that we were dealing with chapter 7.1, there we discussed how we estimate a population proportion. And you're going to see that the process is almost exactly the same. There's just going to be one or two things that we need to talk about, or one or two things that we need to negotiate now that we're switching into population means instead of population proportions. So what we're going to talk about in this section is if we have our hands on a sample mean, so that is if we have information about X bar or a sample mean, how can we use that information to give us a good idea as to what the population mean? So again, remember, we use sample statistics to help us estimate population parameters. This is one of the first things we talked back about at the beginning of the semester. And it turns out that the idea, or the main idea, is again exactly the same thing as we talked about when we were looking at how we can estimate a population proportion. And that is that we introduce error because we're dealing with the sample, and rather than a population parameter. So we're dealing with the sample rather than a population parameter, which means, again, we introduce error. And the amount of error that we introduce is contingent upon two things. It's contingent upon the sample size, which is n, and it's contingent upon our confidence interval. So that is, do we want to be 99% confident, 95% confident, 90% confident? And again, the more confident that we want to be, the bigger our interval becomes. The bigger our sample size is, as our sample size grows, the more precise our confidence interval is going to be, right? The closer we get to the actual population size, which is our true mu, the less error that we have. So I thought of an example that we could use to kind of illustrate this point. And so here's a nice example. A lemonade company claims on average each cup of lemonade that they make has 7 grams of sugar. Okay, you took 15 samples. So what you did is you took 15 cups of the lemonade, and we're going to assume here, even though it doesn't say it, that the sugar distribution in the lemonade, and I probably should have said this right up, but the sugar distribution in the lemonade is distribution normally distributed. It has a normal distribution. Again, that's one of the assumptions we have to make. We're going to talk about that in a second. So we're going to assume that sugar has a normal distribution. We took 15 samples. So we went in and we took 15 cups of this lemonade. And we found that on average, that there was 7.8 grams of sugar. So again, the company claims there's only 7 grams of sugar in each cup. We took 15 cups and we found on average there are 7.8 grams of sugar. And we also know from the company that their standard deviation sigma, now this becomes important. Notice that we have sigma, which means that we have the population standard deviation is equal to 0.19 grams of sugar. So the question is, can we sue the lemonade company for misrepresenting their sugar content per cup of lemonade? And so how can we use our 15 samples to project onto the entire population of cups of lemonade for the company? So we can't get our hands on every single cup of lemonade for the company, but we can get a good amount of information with these 15 samples, again, assuming that we know that sugar has a normal distribution. So these are some things that we can think about. And as in before, we said that we used p hat as our best point estimate of the population proportion. We're going to use x bar as the best point estimate of the population mean. So we're going to use our sample mean as the best point estimate of the population mean. And our sample mean was in our 15 cups, in our 15 samples, that we found that we had an average of 7.8 grams of sugar. Okay, so we're going to do, like I said before, exactly as we did above, which is we're going to figure out how much error there is based on our level of confidence in our sample size. But there's something else here as well. And something that we need to focus on when we talk about estimating a population mean is this idea about the standard deviation. Are we dealing with a population standard deviation, which, as you guys know, is sigma? Remember that when you see Greek letters, we're pretty much talking about a population parameter. Or do we know the sample standard deviation, which is S? And if that's the case, so if we have sigma in one example and S in another example, we're going to use two different formulas. And the reason is this. we know that if we only have information about the sample standard deviation, that there's going to be a lot more error. And again, that's just because you don't have information about the entire picture. So if we use the sample standard deviation with us, then we have more error. If we use the population standard deviation, which is sigma, then we have less error. So we're going to focus on the first case. We're breaking this up into two different cases here. And the first case is, well, what if we know the population standard deviation sigma? So what happens if we know the population standard deviation? What formula are we going to use, and how are we going to convert that into confidence intervals? So what we do have to assume is we have to assume that either the population is normally distributed or that our sample size is large enough. And remember that 30 was the sample size that we're looking for. So assuming we know the population is normally distributed, that's why I had to say up here that sugar has a normal distribution in these lemonade samples that we're taking here. Or if the sample size is large enough, and remember with those two things, we can use the central limit theorem, which allows us to do this, allows us to do confidence intervals with good statistically significant results. And it also is going to allow us to do something called hypothesis testing, which we're going to do next class. So assuming that one of those two conditions are met, then the formula we're going to use, and again, we're going to use this formula when we know sigma, when we know the population standard deviation, is E is equal to Z alpha over 2 times sigma over the square root of n. Okay, and let's make sure that you understand what each one of those variables stand for. E is the margin of error, so E is our error. And hopefully you remember Z of alpha over 2 is our Z critical value. And the reason we call it alpha over 2 is because it's two-tailed. We're going to get to that in a little bit. And that Z alpha over 2 comes from, if we go back up to here where we were talking about with confidence levels, it comes from this information up here. Z alpha over 2 is based on our confidence level or our alpha or a level of significance. So Z alpha over 2 is comes from, again, our level of significance. Sigma represents our population standard deviation. And again, that's something that we're going to give you. So error is what we need to figure out. We need to figure out what Z is, excuse me, what E is. Z of alpha over 2 we're going to give you. And you're going to figure that out based on how confident that we want to be, based on 95% confident, 99% confident, or 90% confident. Sigma stands for the population standard deviation, also something we're going to give you. And N is our sample size. How many samples were we able to get our hands on? So this is the formula that we're going to use to help us figure out how much error that we have. Again, assuming that we know the population standard deviation. And in order for us to construct the confidence interval, remember what we're going to do is we're going to take our sample statistic, we're going to take our sample mean, subtract the error from it, and that's less than the true population mean, and then take our sample mean and add the error to it, and that's going to be the upper bound, again, for the confidence interval for our true sample mean. And over here, but in other words, use our sample mean, add or subtract the margin of error from it, and this represents the confidence interval estimate of mu. So let's take a look at this example. A lemonade company, on average, claims, on average, that each cup of lemonade they make has 7 grams of sugar. So we take 15 samples and find an average of 7.8 grams of sugar with standard deviation. Sigma is equal to 0.19 grams. Construct a 95%, and again, we have to say somewhere in here that that sugar is normally distributed, so that will be in your homework. I just forgot to put in this example. Let's construct a 95% confidence interval to represent the amount of sugar in a cup of lemonade from this company. And then when we're done with that, we're then going to answer the question, is the lemonade company being honest or dishonest with their assessment of 7 grams of sugar? And if that's the case, could you sue them? If you're a lawyer and you're looking for a class action lawsuit, can you come in and sue this lemonade company because their claim that they only have 7 grams of sugar is not true? So here's how we're going to handle this. Again, we look at this and you say to yourself, okay, I'm looking for information about a population mean. So I'm looking for mu. I know our best point estimate is X bar. And X bar in this case is 7.8 grams. All right, so the first thing, once we know what the point estimate is, the next thing we're gonna do is we're gonna construct our margin of error. We're gonna find E. So remember, E is Z alpha over 2 times sigma over the square root of n. So let's fill in this information. The error equals, okay, Z alpha over 2. Well, we wanna be 95% confident. So I'm gonna go back up here and pull up my 95% confident. And 95% confident comes from this Z alpha over 2, it's 1.96. So let's go back down here. Let's plug in that 1.96. So E is equal to 1.96 times sigma, the population standard deviation, which is 0.19, divided by the square root of n. And I hope you can see that n is 15. Okay. Any questions about this so far in regards to this? Just go back and read it over again and make sure that you're comfortable with these three values. Again, Z alpha over 2 comes from that, that two-tailed critical value when we have a 95% confidence interval. Sigma is our population standard deviation, which is 0.19. And n, excuse me, is equal to 15. It'll be the square root of n or the square root of 15. So let's figure out what E is on my calculator. You can do it in one of two different ways on your calculator. You could just multiply, remember, you can multiply your numerators together. So 1.96 times 0.19 and then divide that by the square root of 15. So 1.96 times 0.19 divided by the square root of 15. And I get E is equal to 0.096. Again, we're rounding E to 3 decimal places. All right, ready? So if E is equal to 0.096, let's talk about the information that this example is giving us. So let's go over here to, or the third step of this process, which is going to be, now let's take a look and let's actually construct the confidence interval. So remember what the confidence interval is. We're going to take our sample statistic, which is X bar, subtract the error from it, that's less than the true population mean, which is less than our sample statistic plus the error. So our sample statistic is 7.8. Subtract the error from it, which is 0.096. That's less than the true population mean of how many grams of sugar are in it, which is less than our population mean, which is 7.8, plus the error, which is 0.096. And when we get an outcome for this, 7.8 minus 0.096, I get 7.704 is less than mu is less than 7.8 plus 0.096, which gives us 7.896. Okay, so this is the confidence interval, and let's talk about what this is telling us, or the information that this is telling us, and then we'll go back and answer those questions. So what this is telling us, because we're 95% confident, is 95 out of 100 times, or 95% of the time, the true population mean, sorry, I should say 95% of the time, the true population mean will be between 7.704 and 7.896, which, and this represents, remember, this represents grams of sugar. So that means 95% of the time, if we were to run this statistical test 95 out of 100 times, there will be in the average cup of lemonade between 7.704 grams of sugar and 7.896 grams of sugar. So what does that mean? Well, let's go back and compare it with this statement over here. Is the lemonade company being honest or dishonest with their assessment of 7 grams of sugar? Well, is 7, now remember this is what the company claimed, is 7 somewhere in this region over here? And I hope you can see that it's not, think about this in terms of money. This is $7, this is $7.70, and this is $7.89. $7 is not in the actual mean. So what that's telling us is we have a fair amount of good statistical information that could tell us that this company is being dishonest. They have more than 7 grams of sugar in their average cup of lemonade. And in fact, they have between 7.704 and 7.896 grams of sugar in their average cup of lemonade. So in regards of, can you sue them? Why not? If you're a lawyer, if you're looking to get some money out of it, if you're a good statistician, hell yeah, give them a sue. Give them a sue. I spelled it correctly, give them a sue. You would probably be able to come up with some type of legal implication for this company. Now again, this you have to get your hands on some good statistical information. These 15 samples that you took have to be good SRSs. Remember we talked about that, simple random samples back at the beginning of the semester. So assuming that your statistics are in check, you do have a good legal case. And in fact, this in my head, I don't know if you guys remember, there was a case against Subway, the sandwich company. And you know that song, $5 foot long, $5 foot long? Well, I believe not too long ago, somebody went in and sued Subway because they found out that a bunch of their sandwiches actually were not a foot long, they were smaller than a foot long. And in my head, they kind of hired a statistician or like a regular person went in and hired a statistician and said, measure these sandwiches or the length of these sandwiches, are they more than a foot or less than a foot? And they came out with something like the mean is less than a foot, and they used some confidence interval in it. But you know, who the hell knows if that's what really happened? Okay, so now this is how we're gonna run a confidence interval if we know the population standard deviation, if we know sigma. Now, if we don't know sigma, which is the case most of the time because you're dealing with a sample, right? So we're taking a sample. So most of the time, we're not going to know sigma. So if we don't know, but once we have a sample, we can figure out what S is, so ONCE. Once we have a sample, finding the sample standard deviation isn't too bad, so we can find it. So once we can find the standard deviation, most of the time in the real world, we're not going to use that formula again because it's difficult for us to get our hands on an entire population's worth for the standard deviation. So we're going to figure out what our sample standard deviation is instead. So if that's the case, then we're going to use a different distribution. If we do not know the population standard deviation sigma, and we still have to make those same initial assumptions that we made before, which is the population is still normally distributed or the sample size is large enough, which is greater than 30, then we're going to use the following formula to find the error to help us to create a confidence interval. And we're going to use this. The error is equal to T alpha over 2 times S over the square root of N. Okay, so what makes this formula different than the other formula? Well, in the formula, the first formula we were working with, we had this. E is equal to Z alpha over 2 times sigma over the square root of N. Notice two differences. Difference number 1, S sigma, right? Again, in the formula we used before, we knew the population standard deviation. Here we don't. Here we know the sample standard deviation. Difference in formulas number 2, T alpha over 2, Z alpha over 2. So I want to make sure that you understand the fact, first of all, now the n's are the same, so that n is still the sample size, but I want to make sure that you understand the fact between these two. You know the difference between S and sigma. You need to know the difference also between T alpha over 2 and Z alpha over 2. Now Z alpha over 2 is, and we didn't really talk about where the statistic came from, but it is a Z value. So if you guys remember those Z charts that we talked about before, you can pull those confidence intervals, or you can pull the Z alpha over 2 off of those Z charts. But now we're looking at something that we call T alpha over 2. And T alpha over 2 is the T critical value. So we still have pretty much the same formula. The E is error. T alpha over 2 represents the T critical value. We're going to talk about that in a second. times S, which is the sample standard deviation, divided by the square root of n, which is the population size. Now, T alpha over 2. And again, we use the T distribution if we know S. So here we know the sample standard deviation. Here is how the T distribution works. Okay, let me compare these two. Now, the blue guy over here, this is the standard normal distribution. This is what the standard normal curve looks like if we were to graph it, right? And if you take a look here at the standard normal curve, we have a mean at 0. We have standard deviations, 1, 2, 3, which captures 99% of our data, -1, -2, -3, right? Between, making sure that I'm doing this correctly, between between -3 and 3, we should be able to capture -3 and 3 standard deviations. We should be able to capture 99% of our information. Now, I want you to compare that with the T distribution. Take a look at T. What do you notice the difference between T and Z? Let's take a look at T. Well, T is our thickie. T is fatter than Z, right? Z is taller and skinnier, it's more svelte. T is fatter. So it's one difference between the two. It still has that same general symmetric bell shape, and I hope you guys can see that, but it's like a fat bell shape over here. So students' T distribution also has, and we're going to talk about where the name student came from in a second. It doesn't mean that like you guys are students, it means something else. Students' T distribution is the same general symmetric bell shape as the standard normal distribution, but has more variability, which means it's wider. And we would expect there to be more variability because we have a sample, again, instead of a population. So we're getting a statistic about a sample of the standard deviation rather than knowing information about the population of the standard deviation. So this fattening over here, again, just tells us that there's going to be more error. It's more variability, it's wider, and we would expect that with smaller samples. Students' T distribution has a mean of T equals 0, as does, let me draw this over here, it has a mean of T equals 0, as does the standard normal distribution. However, we're not containing 99% of our data within the 3 standard deviations. T drags on a lot more. It's fatter, 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 fatter. And if you can see here, the standard deviation of T distribution varies with sample size, but it's greater than 1. As our sample size gets, as the sample size of n gets larger, the student T distribution gets closer and closer to the standard normal distribution. So if our sample size, let's say over here that this is a small sample size, this is how fat it looks with like n is equal to 4. If we were to continue with this, if n is equal to 10, it would approach the normal bell-shaped distribution. If n is equal to 40, it looks almost exactly like the regular standard normal distribution. So this happens again with smaller samples, and it also happens because, or the reason that we use students' T distribution is because we're dealing with a sample. And so it's really fat with smaller samples, and it gets tall and skinny as our sample size increases. So we need to figure out how our T distribution works. Oh, let me go back. Students' T distribution was actually named after someone named student. The person's name was student. So again, it's not one of you guys, it's just a person that founded this distribution, and they noticed that, you know, even if you didn't have information about the entire population, that you still had this symmetric bell-shaped curve, but it was just much thicker on the end and not as high and peaked in the middle until your sample size got bigger and bigger. So let's talk about how we can find our T alpha over 2 or the T critical value. So what I didn't tell you guys, but what I should have told you, and if you don't have this now, grab your hands on it. If you guys head into Blackboard, there will be critical values for students' T distribution chart up there. I copied and pasted it right onto this document so you can see it's right under here. So even if you want to print this out, that's absolutely fine. I want to make sure that you can figure out how to find the T alpha over 2. The Z alpha over 2 is fixed. T alpha over 2 is not fixed, again, because it depends on sample size. So remember what's going to happen if we have a small sample, it's going to be fat and wide. as our sample size increases, so we're getting more of a sample, it's going to approach the standard normal curve. So T alpha over 2 is based on sample size. So let's make sure that you can find these critical T values. That's what that means, based on this information. So let's take a look at this first example. A distribution has a sample size of 12 and you wish to be 95% confident. So let's talk about how to find T alpha over 2. We're gonna go over here. All right, first of all, we see over here for critical values for students' T distribution, there's something called one-tailed area and two-tailed area. Confidence intervals are always going to be located under two-tailed area, and that's why we call it T alpha over 2. There's two tails. You get a tail on the right-hand side and a tail on the left-hand side, and we're looking at this area in the middle. So for confidence intervals, we're always going to use this second row over here. All right, so let's talk about how to find these values. So we're looking at a sample size of 12 and we want to be 95% confident. I'm going to write that down over here to remind myself so I don't have to keep going over and over to it. Let's take a look at the sample size of 12. Well, we're going to use this column over here to help us with the sample size. And this DF, it means degrees of freedom. Degrees of freedom, it's sample size minus 1. That's all it means. So remember, the degrees of freedom over here is a sample size minus 1. So if we have a sample size of 12, our degrees of freedom is 11. So we're going to look over here in this row over here with 11. Now, the next thing we need to do is we need to use 95%. We want to be 95% confident. Remember that that means that our alpha level is 5%. So alpha is equal to 0.05. Alpha is the same thing as saying 1 minus our level of confidence, or 1 minus 0.95. So if we want to be 95% confident, our alpha is 100% minus 95%, which is 0.05. So we're going to go over here to where it says two-tailed area, and we have 0.05, which is here. And we're going to figure out where these two values meet, where we have an alpha level of 5%, and we have a sample size of 12, which means 11 degrees of freedom. And it right over here, 2.201. So our T of alpha over 2 is 2.201. Okay, let's do a few more examples of this just to make sure that you understand how this works. T alpha over 2. In this example, it says a distribution has a sample size of 28 and you wish to construct a 98% confidence interval. Okay, sample size of 28 and you wish to construct, hold on, let me erase these guys, a 98% confidence interval. Okay, sample size of 28, and there, I think I said it was 98. So n is equal to 28, and we have 98%. Okay, so n is equal to 28, which means, again, we're dealing with n minus 1 degrees of freedom. So we have 27 degrees of freedom. So our answer is going to be located somewhere over here, somewhere in this region. 98%. 98% comes from this over here, because remember that 1 minus 0.98 is equal to 0.02, or another way you can think about it is 100% minus 98% is equal to 2%. So this is the column we're looking at. And again, we're always going to use this row over here, the two-tailed area. So let's go down with 0.02, and where that meets 27. And we're right over here at 2.473. So our T alpha over 2 is 2.473. We're getting the hang of it. Let's do 2 more examples just to make sure you are. The next example, you have a sample size of 46 and you wish to construct a 99% confidence interval. Let me erase all these guys. Okay, sample size of 46, 99% confidence interval. So n is equal to 46. And we have a 99% confidence interval. Okay, so n equals 46. Let's take a look over here. N equals 46. And when I go and I look over here, 46 minus 1, right? 46 minus 1. This is our degrees of freedom, which is, again, exactly the same thing as saying n minus 1. 46 minus 1 gives us 45. So we're right over here. 45. Now notice, let me check one thing. Notice there are some cases where, let's say we ended up with, or let's say we had a sample size of something like 78. Well, 78 minus 1 gives us 77. And if you take a look over here, there is no degrees of freedom for 77. But if we read down here, for degrees of freedom not found in the table, use the closest degrees of freedom that's smaller. So if we have 77, we'd go the degrees of freedom, the closest that's smaller, which is 70. That is because we want to be extra careful. We'd rather add a little bit of error to our estimate, or we'd rather be more careful with our answer. So this is telling us we're going to have, it's possible we're going to have a little bit more error because we don't have the exact degrees of freedom there. So you always want to choose the degrees of freedom that is smaller. In this case, we actually happen to land on the degrees of freedom that's located here, which is 45. 99% confident means we have an alpha level of 0.01. Again, think about it, 100% minus 99% is 1%, and 1% is 0.01, which is over here. We're gonna go down this guy. We're gonna go across this guy, and we have 2.69. So T alpha over 2 equals 2.69. Okay, one more example. You have a sample size of 7 and you wish to construct a 90-degree confidence interval. Let's talk about how we would do that. Sample size 7, 90% confidence interval. Okay, sample size of 7 means that we have 6 degrees of freedom. Right over here, 6, ooh, just kidding. Here, sample size of 7 means we have 6 degrees of freedom. Again, it's n minus 1. 90% confident means that we have an alpha level of 0.10, or again, 100% minus 90% gives us 10%. As a decimal, it's 0.10. So here's 10. These two intersect. Here's here, here's here. They intersect right here at 1.943. So T alpha over 2 equals 1.943. All right, so now that you're comfortable with reading these charts, let's finish with doing 1 or 2 examples of how we can construct confidence intervals given information about knowing the population standard deviation rather than, knowing the sample standard deviation rather than the population standard deviation. So in the next few examples that we're gonna do, you're gonna notice that we're gonna give you information about S. Anytime, again, that you know the sample standard deviation, to figure out what the error is that's involved here, we're going to say that error is equal to T alpha over 2 times S over the square root of n. Anytime we know the population standard deviation, we're going to use the formula sigma over the square root of n. But we're really going to focus on this bit over here because you guys already know how to use the Z table. I showed you how to do that. Now we're going to talk about how to use the T table. So let's take a look at this first example. In a group of n equals 63 baby boys born, their mean birth weight is X bar equals 7.87 pounds with S equals 1.07 pounds. Construct a 99% confidence interval for the mean birth weight of all baby boys. Okay, so let's say that this is taking place in a particular hospital, and the particular hospital over a week found that of the 63 baby boys that were born there, their mean weight is 7.87, and they have a sample standard deviation, this is the important part, with 1.07 pounds. Let's construct a 99% confidence interval for the mean birth weight of all baby boys. So E is equal to T alpha over 2 times S over the square root of n. Well, before we get there, the first thing you should know is that our best point estimate for this is 7.87 pounds, right? That's the information that we have. So we're going to use the fact that we know that the mean is 7.87 pounds, and we're going to use that to help us figure out what the true population weight of all baby boys could be. Okay, so let's figure out what the error is. So step 1 is you identify what a good point estimate would be, and here it's 7.87 pounds. Step 2 is, okay, well now let's figure out what the error is. An error is equal to T alpha over 2 times S over the square root of n. And again, we're using this formula up here because we know the sample standard deviation and not the population standard deviation. We know that S, so I'm going to start with this bit, S is equal to 1.07. We know that N is equal to 63. right? Because N is our sample size, and we have a group of 63 babies. And T alpha over 2. Okay, so let's go to T alpha over 2. We're going to figure out what that is. Well, our N is 63, and we want to be 99% confident. So 63, we have an N of 63, and we want to be 99% confident. Let me erase this little guy over here. N is 63, which means that we have 62 degrees of freedom. Notice 62 is not found on here, so we're going to use the closest degrees of freedom that's smaller, which is 60. So we're over here. 99% confident means we have an alpha level of 0.01. 100% minus 99% is 1%. So we're going to use this column down here, right? And again, we're using this guy. Let's see where these two guys intersect each other. Right here. Coming across here, we're right here, and we end up with 2.660. So this is 2.660. Okay, so error is equal to 2.660 times 1.07, and then we're going to divide that by the square root of 63. And we get 0.359 rounded to 3 decimal places. So 0.359. Okay, so here's our error. Step 3 is let's construct a confidence interval based on this. So remember, the confidence intervals are sample mean minus the error. That's less than the true population mean. And then we're going to take our sample mean and add the error onto it. Sample mean is 7.87. Subtract off the 0.359 pounds of error. That's less than the mean. Is less than 7.87 plus 0.359. And then kind of combining these two together, 7.87 minus 0.359. Oops, sorry, I'm gonna try that again. 7.87 minus 0.359. We get 7.511 is less than the mean, is less than 7.87 plus 0.359, which gives us 8.229. And this is in terms of pounds, so whatever unit you use, we're going to be consistent with it. So in regards to this, construct a 99% confidence interval for the mean birth weight of all baby boys born in this particular hospital or in this particular situation, whatever it is. We would say 99% of the time, the true population mean, or the true weight of all baby boys will be found in the interval 7.511 pounds to 8.229 pounds. Okay, and this is 99 out of 100 times, it's 99%. 1% of the time it's not going to be in here. Remember, there's always going to be some error unless we make an obnoxiously large confidence interval, and that's not going to give us much information, right? If I said that we're 100% positive that baby boys are going to weigh between 0 and 1,000 pounds, well, that's true, but that's not going to give us any type of good scientific information. So 99% of the time, we know the true weight of all baby boys, the population of all baby boys born in this situation will be between 7.511 pounds and 8.229 pounds. Pretty cool, huh? Let's take a look at, we have 2 more examples to talk about here, so hang in with me, you guys are doing great. I just want to make sure that you're comfortable with this process. This should look familiar. A lemonade company claims on average, each cup of lemonade they make has 7 grams of sugar. You took 15 samples and found an average of 7.8 grams of sugar with sample standard deviation S equals 0.19. So this is exactly the same question we were dealing with before. This time, instead of knowing the population standard deviation, we didn't know that for this example, we just knew the sample standard deviation, right? And you can always figure out the standard deviation, what the standard deviation is if you're given a sample. This is what we talked about earlier on in the semester. Let's construct a 95% confidence interval to represent the amount of sugar in any given cup of lemonade from this company. Again, because we have S, we're gonna use this formula. E is equal to T alpha over 2 times S over the square root of M. So we're gonna start off, the best point estimate of this is 7.8 grams. Okay, and so for our sample, T alpha over 2, for our, we're gonna use this formula. So I'm gonna start filling information that I know. I know that S is 0.19. I know that N is 15. Okay, we need to figure out what T alpha over 2 is. And again, I'm going to use students' T distribution because I don't know the population standard deviation. So T alpha over 2, we need to figure out. So we want to be 95% confident, and we have a sample size of 15. So 95% and 15. Let's write this down, 95% and 15. Let me erase some of these other guys. 95% and 15. If I don't keep repeating it, I won't remember. This is what happens when you get old. N equals 15, 95%. Okay, so N equals 15 means, again, remember at N minus 1 or 14 degrees of freedom, so we're right over here. 95%, 100% minus 95% would leave us with 5%. So we're gonna figure out where these two intersect. Right here, and 14. They intersect right here, so our T alpha over 2 is 2.145. Okay, so let's figure out what that value for E is. 2.145 times 0.19. Divide that by the square root of 15. And we have 0.105, again, rounded to 3 decimal places, 0.105. All right. Now let's figure out what the actual confidence interval looks like. And again, on your way to finding the confidence interval, the first thing you want to do is you want to find the best point estimate. That's number one, and then find what your error is because you're using a sample. So X bar minus E is the same thing as saying 7.8 minus 0.105 is less than the true population mean. Is less than 7.8 plus 0.105. Okay, so 7.8 minus 0.105 minus 0.105. Oops, on that end, that'll give us 7.695. That's less than the true population mean, which is less than 7.8 plus 0.105, 7.905. And so what this is telling us, again, because we're dealing with a 95% confidence interval, is 95% of the time, 95 out of 100 times, the true amount of sugar per cup of lemonade is between 95 out of 100 times, the true amount of sugar per cup of lemonade will be between 7.695 and 7.905. This is 95 out of 100 times it will be located in here. 5 out of 100 times, maybe it's 8.1. Maybe one of them is 7.0. Maybe we got a particularly small sample. But again, most of the time, our range of values for the sample mean of the amount of, for the population mean of the amount of sugar per cup of lemonade, that would be between 7.695 cups and 7.905 cups. Okay, let's end with one more example. And this last one says, in a test of weight loss, a sample of 27 adults used the Atkins weight loss program. After 12 months, their mean weight loss was found to be 2.1 pounds with standard deviation of 4.8 pounds. Construct a 90% confidence interval for the mean weight loss of all subjects. Does it appear to be an effective weight loss system? Why or why not? First thing I'm going to notice is I see this word sample. So it doesn't tell me anything about the standard deviation, right? It doesn't say sample or it doesn't say population. But once you see that you're dealing with the sample, it's assumed that this is a sample as well, that the standard deviation is going to be a sample as well. So our best point estimate for the amount of weight loss using this, the mean weight loss was found to be 2.1 pounds. And again, because we're dealing with the sample, we're going to use the formula E is equal to 2 to figure out what the error is. E is equal to T alpha over 2 times S divided by the square root of M. Okay, so S, standard deviation, we know is 4.8 pounds. N, we know is equal to 27. We had a sample of 27 adults. T alpha over 2. Okay, T alpha over 2. We have a sample size of 27 and we want to be 90% confident. So a sample size of 27 and we want to be 90% confident. Sample size of 27 and we want to be 90% confident. Sample size of 27. Sample size of 27 means that we have 26 degrees of freedom. We want to be 90% confident. Okay, so 90% confident means to think about 100% minus 90% gives us an alpha level of 10%. And we're always going to be here for confidence intervals for two-tailed areas. That's again why they call it T alpha over 2. Let's see where these two intersect. So it's 26, 10. And we have a critical T value here of 1.706. So that's 1.706. Okay, so let's figure out what that numerical value is. So we have 1.706 times 4.8. And let's divide that by the square root of 27. And we have 1.576 rounded to 3 decimal places. So E is equal to 1.576. Okay, so for step 3, let's actually construct the confidence interval, and the confidence interval is X bar, which is 2.1 pounds. Well, let me write down the formula first. And I find it's a good habit. I'll give you a little hint to making sure that you kind of learn mathematics and you understand these formulas. The more you write them, the more they'll just start sticking in your brain. So I write them over and over again, and they stick in my brain for a long time. Just something to do with that muscle memory and on your hand of just writing down that formula. Okay, so X bar minus E is less than mu is less than X bar plus E. So X bar is 2.1. So 2.1 minus 1.576 is less than the mean, is less than 2.1 plus 1.576. Give me 1 second, I'm just checking my math over here. Okay, I'm happy with it. So 2.1 minus 1.576, which is 0.524, is less than mean, is less than 2.1 plus 1.576, which is 3.676. So let's talk about what this means, and then let's answer the question, does it appear to be an effective weight loss program? Why or why not? So what this is telling us, again, because we're dealing with a 90% confidence interval, is 9 times out of 10, or 90% of the time, the true population mean, which means the true amount of weight lost will be contained in this interval, 0.524 pounds, and 3.676 pounds. Okay, so let's talk about what this means. Would you go on a diet if you had a 90% chance of losing between half a pound and 3.6 or 3.7 pounds? Right, so going on a diet and coming off of the diet, going on a fairly intense diet, because that's what the Atkins diet is. This is the Atkins weight loss program. Going on a diet and coming off and really only losing half a pound, 0.524 pounds, or losing 3.7 pounds, that to me is not worth it. Now, it's entirely up to the person. But I think if you're paying all this money to go on a diet, does it appear to be an effective weight loss program? I mean, you are losing weight, but the amount of weight that you're losing here is minuscule. And remember, this is only 9 out of 10 times. 10% of the time, it's going to be outside of this region. So it could be on occasion you're losing 4 pounds or 5 pounds, or it could be on the occasion that the average person is losing 0 pounds even, right? Because we're less than 0.524. But in regards to answering your question, does it appear to be an effective weight loss program? No. I mean, half a pound to go into like an intense weight loss program is not it's not a meaningful weight loss. So this is it for chapter 7.2. And what I really want to make sure is that you understand when we use which formula. And keep in mind that we use this formula, E is equal to Z alpha over 2 times sigma over the square root of N, when we know sigma. And when we don't know sigma, and saying that you don't know sigma means that you do know S, and we can figure it out. Then we're going to use the formula E is equal to T alpha over 2 times S over the square root of N. So we use student's T when we know the sample standard deviation, and we use a regular Z chart when we know the population standard deviation.